Alright, so for the last part of our motion unit, we should be dealing with our famous Vat equations. So we've got those four equations. You should have all of them in your booklet, in your data booklet, so you don't have to memorize them. However, obviously, as you're using them, you eventually remember, right? So the unknowns that we have been dealing with those so far, and you should know what they are, but basically S stands for displacement or distance, U is usually the initial velocity or speed, V is the final velocity or speed, A is the acceleration, and T is the time taken. So let's just apply this to one example. So we have a driver here of a car which is traveling at 25 meters per second. Usually, let's just stop here for a minute. Usually when we're dealing with problems, kinetics, motion, forces, it's usually very important, and it helps a lot if you just write down what you know out of those unknowns. So here we're given some speed. Well, we don't know if it's initial, if it's going to change, but it's the initial speed. We don't know if the final one's going to be the same, but so far it's the initial. So a driver drives along a road and applies the brakes. So we're expecting our final speed to be 0, right? Let's see. So the car comes to a stop, yeah, in 150 meters. So we know that the final speed is 0, and our displacement is 150 meters. Alright, so far so good. Now, there's a uniform deceleration. So this means that the acceleration, this is being called deceleration just because it's stopping, right? But basically, it's uniform, so it doesn't change. There will be a value, it will be constant. We could get, if this was a graph, it would be a nice straight line in our velocity time graph, but obviously it would be decreasing, so it would be something like that, right? Our initial value would be 25. This is velocity time, and we don't know the final time. So let's see, calculate A, the time that the car takes to stop. So it would be exactly this point in the graph, and the deceleration of the car, which would be the gradient. So let's take a look at our equation. You don't need this graph for this question. Let's take a look at the equations that we have. So we know initial and final velocities, or, well, speeds, because the direction here doesn't matter, and we know displacement. So since we're looking for the time, we should look for an equation in which we have time. However, there will be some equations in which we have things that we don't know. For example, in the first one we have acceleration, which we don't know. On the second one we also have acceleration, which we don't know. On the third equation we don't have time. So the third one will be the one we're going to use for time. So we know displacement, we know both speeds. So taking that equation as equals, I'm just going to copy it here for a minute. So u plus vt over 2. Now, we want to find time, so we can rearrange this equation. So before you put any numbers in, let's just rearrange. So it's going to be 2 times displacement, so time. Take a look, time is going to be alone. 2 is going to multiply displacement on the other side of the equation, and the sum of the velocities will divide. So I've made t my subject, and now I can put my values in. So that would be 2 times the displacement, which is 300 meters, over u plus v. Since v is 0, u is 25 meters per second. Alright, now if we divide 300 by 25, we should find 12. I believe so. So 12 seconds. Right, so far, so good. Now, to find the acceleration, we can actually now choose. We can pick different equations. But let's see which one is probably the easiest. I don't know, either this one, right, or this one. I don't know, either one. Let's pick this one. So I've got that my final velocity squared equals my initial speed squared. So both speeds or velocities here we're not caring about. So it's just the magnitudes of those velocity factors plus 2 times a times displacement. So here we don't have time. We could use this equation straight away if we wanted to find the acceleration and we didn't want to find out the time. This is A, this is B. So this is 0, right, and this is 25 squared. So 0 is equal to 25 squared plus 2 times some acceleration that we don't know times 150. So this is going to be 300, which is equal to 25 squared. Therefore, our acceleration will be 25 squared divided by 300. Now, since our speed is in meters per second, our displacement or our distance is in meters, this will be in meters per second squared. So we don't have to worry about the units. Oh, this is negative. This is negative, and this is also negative. So that's, well, that's a deceleration, isn't it? So if we get the values, we should have a negative 2.1 meters per second squared. So that's a fairly simple example, right? And the minus sign here shows us that the car is decelerating rather than accelerating. If this was positive, it would mean that the speed is increasing each time. If this was a vector, then this negative sign would mean something else. It would mean that it's direction where it's going to. So it would decrease the speed at first, but remember, it would accelerate on the opposite direction later. Now let's take a look at another example now. So let me get rid of this, and there you go. So a cyclist slows uniformly from a speed of 7.5 meters per second to a speed of 2.5 meters per second in a time of 5 seconds. So U is 7.5, that's our initial speed, meters per second. V is equal to 2.5 meters per second, and our time, elapsed time, is 5 seconds. So meters per second, seconds, everything in SI units. So we don't have to worry about changing units here, right? So calculate the acceleration. Now for this, in this case, if we take a look at our equations, the easiest one is the first one, right? So V, we can rearrange that equation, but let's just copy first. So V equals U plus AT. This only works if our acceleration is uniform, okay? Now, A would be V minus U divided by T. So our final velocity is 2.5. Our initial velocity is 7.5, so we can see that the difference is going to be minus 5. And this over 5. So this is in meters per second, this is in seconds. Our result will be in meters per second squared. So that's negative 5 over 5, so that's going to be negative 1.0 meters per second squared. Now, let's actually appreciate some important information here. You might ask yourself, why am I putting 0.0? Why am I not just putting negative 1? Well, if you take a look at the numbers that you had in the beginning, all of them were given up to 2 significant figures, right? And, well, 2 significant figures, and all of them 1 decimal place. So we should try and keep the same number of significant figures. If we just put negative 1, it's implied just 1 significant figure. Alright, if you put 1.0, then it's implied that it's 2 significant figures. It's implied that you know that this is a 0. And obviously, if you look at the numbers that we have here, we are pretty confident that this is a 0. Perhaps what's coming after might be some weird numbers that we don't know, and then what comes after the 0 will be very uncertain. But this 0 here is something that we know that it's at least close to 0. If we round, it would be 0. Okay? So that's why we're putting this negative 1.0. So this is question A. Now question B, what is the distance moved in the 5 seconds? If we had a graph, an velocity time graph, we could just get the area of the graph. So you could, if you wanted, you could plot this graph. You would have an initial speed of 7.5. I'm not caring about keeping this up to scale exactly now, just sketching a graph. Okay, so let's say this is your deceleration, right? And then this is velocity time, and this time here would be 5. So if you calculate the area of this graph, you should get your distance. But let's use the equations first. So if we want to find out distance, if we use this equation here, the last one, we would need time. We don't have time. Oh, we do. So we can use it. So distance would be v plus u, so that's 7.5 plus 2.5 over 2 multiplied by the time, 5 seconds. This is in meters per second, this is in seconds, so our result will be meters. So 7.5 plus 2.5, that's 10 times 5, 50 divided by 2, 25 meters. If we work out the area, we can split this into a triangle and a rectangle down here. So let's call this A1 and let's call this A2. So using A1, we would have this area to be, this difference here is 5, right? If you copy the triangle down here, that's awful. Okay, so let's say that this is our triangle, and then we'll have this length to be 5 and this length to be 5 as well. So the area would be 5 squared over 2. Area 2 would be the rectangle. The height is 2.5 and the base is 5. So it's 5 times 2.5, which is the same thing, isn't it? Both areas are going to be the same. So if we add them up, we should have 2 times 2.5 times 5. Okay, and that would be our displacement. Now 2 times 2.5 is 5 times 5, 25 meters. So there you go, 2 different ways to solve the same thing. That should be it with our Vat equations. There will be some different applications. When we're working with free fall, we're going to have an acceleration that we know, which is the acceleration of gravity. But regardless, it's the same thing. Just looking for what you know, what do you want to find out, which equations are going to lead you into that. And also remember that all those 4 equations that we see on the left over there, they are all in your booklet, so you don't have to memorize any of them. Okay? And that's it.